So sad. Okay, so we're going to wrap up 2.3 and 2.4 today. Still a lot of more conceptual stuff to get through, but once we get through that, things are going to actually start moving pretty quickly, because we're going to derive a bunch of formulas to be able to take derivatives very quickly without going through the limit definition, and we're going to start moving quick. But I still want to just go slowly over some concepts that are going to be important in the future, especially in terms of applications. It's worth summarizing a little bit. Just recall what we know so far. We know about a function called f prime of x, which is defined in terms of a limit, f of x plus h minus f of x over h. This guy's the derivative of f. And basically what it does is it tells you about the slope of f at x, which is another way of saying the slope of the tangent line to f. At x, which can also be interpreted as a rate of change of f. So this was the derivative. It's a very important function. Half of calculus is about this function. It's called the derivative. What it does measure is it measures the slope of your function, or you can think of it measuring as the slope of the tangent line to your function. Tangent lines are super important because they help us approximate functions, because straight lines, we know everything about straight lines. Straight lines are easy to use and compute things with. So if you have a crazy function that's hard to deal with, at a certain point that you want to zoom in, you can just use a tangent line there instead of the function itself. And so if you zoom in and the function starts to look like a straight line, it means you can put a tangent line there, and the straight line can approximate what the function is doing. We can also talk about slope as a measure of rate of change. We mentioned that before. So that the slope of the tangent line can be thought of as how fast the function is changing. So we've looked at all of that so far. So that's what the first derivative was known for. That's why it was developed, to solve the rate problem, figure out how fast something is changing, and it does that by generalizing on what it means to take a slope. We also looked at the second derivative. So this second derivative, this was basically the derivative of the derivative. And that gave us a lot of ideas as well. That one told us how fast the slope was changing. So that's like the slope of the slope. So, and we talked about one application in terms of motion, where we were talking about, you know, the position, if you differentiate, that gives you speed or velocity. It gave you velocity, but if you want to figure out how fast the speed itself is changing, that was acceleration. That was actually the second derivative. It also tells you about things called concavity and inflections. And we kind of talked about what those interpretations might mean. To know, it's really talking about how something is bulging. So if you're bulging inwards or outwards, if you shape like a smile or a frown, it can mean different things. This guy means your slope is increasing and the function is increasing at the same time. Here your function is increasing, but the slope itself is decreasing. So you're increasing but at a decreasing rate. So when you go to that level of analysis, you use the second derivative, and we will talk more about using that later on. But so far that's kind of what we're up to now. So we've discussed limits, and then we looked at a special limit which was called the derivative. This helps us answer the rate problem by measuring slopes of tangent lines. The second derivative tells us how this function is behaving, and that can have all other applications. What I want to talk about now is sort of, well, let me also mention this in my last class, so let's just mention it here. Notations f prime of x, or I can say f prime or y prime, or whatever letter I'm using. I can say dy dx, or I can say something like d dx, and I write the function beside it. These are all notations for the first derivative. If I have f double prime of x, or f double prime y double prime, or d squared y dx squared, these are all notations for the second derivative. We'll talk about why each function is important a little bit later on today, but these are the notations. I'll mostly use the prime notations as I mentioned, but these are other valid notations as well. The guys with the notches, the apostrophes, those are the primes. Those are the notations attributed to Isaac Newton, and the fractional notations, the differential notations. These are attributed to Leibniz, both of which were accredited with developing modern calculus independent of each other. Now I want to discuss when this all sort of breaks down. When can we not use calculus? In other words, at least differential calculus. So in other words, when would a derivative not exist? Might not be something you've considered, but it is possible. Derivative is a limit. So it is possible for it to not exist. Because limits cannot exist. So let's discuss some situations where a derivative will not work. Let's do an example. So let's look at a function not particularly complicated. Absolute value of x is the function we're going to be looking at. We're going to find this derivative at the point where x equals 0 using the limit definition. So let's just jump into this side. We've beaten this to death so far, so let's just run through it. This definition should be burned into your brains at this point. F of x plus h minus f of x all over h. This is how we define f of x. This was the first problem on your quiz. So we're going to actually plug in 0 for x because we care about the derivative at 0. So we're going to look at the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. So if my f of x is absolute value of x, what is my f of 0 plus h?
0, well.
F of x is absolute value of x. What is f of 0 plus h? Yeah?
It's the absolute value of h.
Yeah, absolute value of 0 plus h. Just replace all x's with whatever is inside, right? That's never going to change. F of blah is just going to be you replace all x's with blah. Okay, so that's that. What's absolute value of 0? 0. And this 0 plus h is just h, so this really comes down to be the limit as h approaches 0 of the absolute value of h over h. Now the question is, what is that limit? So apparently we're dividing by 0, but there seems to be an h on the top that we can work with. But let's remind ourselves a little bit here. How do we define absolute value of x? Yeah?
You take a value, you put it into your absolute value equation, and you always get a positive
sure. What does it look like?
It's a V.
It's a V, right? So it comes like this and goes up like that. So what if you plug in a 2 into absolute value? What do you get? 2. What do you plug in 3?
3.
7.
7.
Right, so if you plug in any positive number, you get the number itself, right? So what is the equation of this?
X.
Y equals X, right? The output is the input. However, if you plug in a negative number, you plug in negative 2 into absolute value of X, what do you get? You get positive 2. So if you have over the negative, what it does is it takes the negative of the negative, and so your output is going to be the negative of your input on this side. So your absolute value of X is actually a piecewise function. It's X if your X is positive. It's minus X if your X is negative. Right, so it's a piecewise function. Based on whether your input is positive or negative, it will change its value. Now, we are approaching 0, right? Which means if we're approaching 0 from the left versus approaching 0 from the right, there are 2 different functions to consider here. So this guy, if I try to figure out what this guy is, let's actually see if that's reconcilable. If I'm approaching h from the left side, then my absolute value of h just gives me negative h. That would cancel, that would give me a negative 1. If I'm approaching 0 from the right side, my absolute value of h just returns h. That would cancel, and that gives me positive 1. So if I'm approaching from the left, I get negative 1. If I'm approaching from the right, I get positive 1. What does that tell me about the limit as h approaches 0? It doesn't exist. But this is not some random limit. This is the limit to compute the derivative of this function. So if that limit doesn't exist, it means the derivative doesn't exist. Does not exist at this particular point, at x equals 0. It of course exists elsewhere, because I mean the slope here is clearly 1, the slope there is clearly minus 1. So as long as we're not at that point, the derivative will exist, but at that point the derivative doesn't exist. Right, so this is an example, it's a very standard example for when the derivative does not exist. This is a nice example because the function is continuous there, it exists, but the derivative itself doesn't exist. So computationally we can see that the limit doesn't exist, but really what happened? Graphically we can see the following happened. We couldn't draw a tangent line, was the point. If you see a function with a sharp corner, what is the tangent line through that point? You can draw a bunch of straight lines through that point, but none of them will actually serve as a tangent line, because what is a tangent line? It's an approximation to the function, meaning when I zoom in farther and farther, the function and the straight line should start to look closer and closer together. But it turns out if you zoom in on a sharp point, it will always look like a sharp point. It will never actually start to look like a line. Sharp points are bad. There's no real tangent line. There's no line that you can draw through a sharp point to approximate that sharp point. A sharp point is never going to look linear no matter how much you zoom in. And so the derivative didn't exist because we couldn't actually draw a tangent line. And the derivative is all about finding the slope of the tangent line. There is no valid slope to draw a line. So i.e., we can't find a derivative if we can't draw a tangent line. This leads to 3 cases. does not exist. In one of the cases, we will be able to draw a tangent line, but it won't satisfy the equation of lines that we're used to. Case 1, where a derivative does not exist, is at a point where there is, as we've seen with absolute value of x, a sharp corner. It's called a cusp. That's what math people call a sharp corner. Sharp corner. So if you have a function doing this, or if you have a function doing that, anything with a sharp corner, you cannot find a derivative there. Right? So there is no derivative at this point. There's also no derivative at this point. Because no matter how much you zoom in on a sharp corner, it will never look like a straight line. That's one situation where you can't find a derivative. There's another situation where you can't find a derivative. You can't draw a tangent line to a point if there is no point there, basically. At a point where f is discontinuous. Not sure if I've used that word before. It just means not continuous. That's the negation of continuous. So if you have like a hole or some sort of jump, if you have like an asymptote, you're not differentiable at any of these points, because how are we going to draw a tangent line to a point? There's no point there. There's nothing to draw a tangent line to. So we're not continuous if there's a gap or a hole or a jump or any break in the graph, and if there's a break in the graph, we can't draw tangent lines to the graph. So sharp corners are a problem, gaps are a problem. There's a third case that is a problem, which we're not going to see very often, but it is something I should tell you about. At a point where there's a vertical tangent line. Some functions, they have this weird behavior. They can be doing their thing, and they have an inflection at a point, and they do something like that. And so for a split second, they pass through a point in such a way that the best tangent line to that point is actually a vertical line. If you zoom in, the function will start to look vertical and more vertical. It can't stay vertical for more than a single point because it will fail the vertical line test and it wouldn't be a function. But you have functions that do this kind of weird behavior, like a really fast inflection point, where the tangent line that models that is a vertical tangent line. So in the cases where there's a vertical tangent line, we know that slope is undefined for a vertical line. But the derivative is the slope. So the derivative is undefined here. So at sharp corners, at gaps or holes or places where we're not continuous, or at places where the function does this weird inflection where there's a vertical tangent line, the derivative will not exist. The limit definition, it won't pan out. And if you try to compute it, the numbers, they won't work out, it just won't. This is something you should be aware of, though we're not going to spend a lot of time on it. We mostly care about where calculus does work and where applying calculus. But it's good to know where it doesn't work. In terms of something that I might test you on, a testable material here. I'd really test you on these ideas that I just mentioned about where the derivative doesn't exist graphically. So I'll give you a graph and I'll say something like, tell me where the function is differentiable or where it's not differentiable, or where can you find a derivative, where you cannot find a derivative. Let's do continuous first. Find out the points where it's not continuous. And points where it's not differentiable. I know why doctors have bad handwriting. The longer I teach, the worse my handwriting on the chalkboard becomes. Eventually you're just like, oh my god, can I just stop writing this word already, please? Oh, okay, so not differentiable means you can't find a derivative. I don't know if I defined that word, I don't think so. Can't find where derivative does not exist. So if I can't take a derivative there, I say it's not differentiable there. It's more of an adjustment. Okay. So let's say I would ask that question and I would give you a picture. So it might seem something like this. It's supposed to be a semicircle. Here's my f of x, where its domain is greater than or equal to 0, so I'm forgetting about the negatives. This is 1, this is 2, 4, so there's 2, so 6, 8. This is 11. Where's our function not continuous? Yeah?
At 9, 2. I'm sorry, 9, 4.
Well, at x equals 9 in
X equals
general.
9.
So here I have both a hole and a jump, but either one is good enough to like not make it work. So it's not it's not continuous at x equals 9. Anywhere else?
X equals 11.
X equals 11, there's an asymptote, so the function can't touch it. In order to draw this graph, I have to lift my pencil off the page to jump over that asymptote. So at x equals 11 is also a back point for continuity. But pretty much anywhere else, I can just keep drawing without lifting my pencil off the page, so it's continuous everywhere else. What about if it's not differentiable? So the first thing you should realize is that points of discontinuity are automatically points where we're not differentiable. So you can literally just copy these numbers. Whatever answers is to this question will also be answers to this question. So x equals 9 and 11 right away would come down here, but they might be others. Differentiability is harder to attain than continuity. Are there other points where I can't find a derivative?
Where x equals 2,
Why? Why?
because it's a sharp point.
It's a sharp corner at x equals 2. Right? I'm a horizontal line and then I break off into a semicircle. That creates a sharp corner, right? No matter how much I zoom in, that's never going to look like a straight line. So x equals 2 is a point where you can't find a derivative. Anywhere else? Yeah?
X equals to 6.
6, same reasoning. It's a sharp corner. Anywhere else? No, that's it. Everywhere else we can find derivative. So sharp corners are bad, points of discontinuity are bad. But everything else is good. So that might be a kind of problem I would ask on a test. And of course, I'd ask you to justify these points. So you'd say, why is it discontinuous? You can say x equals 9 because there's a hole. And then you can say, why is it differentiable? You can say x equals 2 because it's a sharp corner. Still some more concepts to get through. I want to do now a kind of summary of the functions that we've looked at so far. Kind of in a table format like was on the quiz. So it's just us re-looking at what each function tells us. Something that's going to be very important for applications later. And it'll also make a lot of things that I'd be telling you make sense when I tell you, oh, this is because of that, and then it makes sense. Oh, yeah. So we're going to do a big table here. Once we get through these concepts, things are going to start moving pretty fast because then we're going to learn all sorts of shortcuts to do stuff. And we're really going to be able to do a lot. So I'm going to put the kind of function in this column. What this function tells us about, I'm going to put in that column. And finally, how. So different functions have different purposes, and so they give us different information, and we want to know how to extract that information. So let's look at the original function f of x. We're no strangers to functions, so we all know what functions do, so let's just fill this one in pretty quickly. This guy gives us outputs for a rule. Right, so if there's a rule that gives me a single output for each input, I can use the function f to figure that out. It also it helps us figure out points on a graph. So if you ever need to figure out the output of some rule, or if you ever need to find the points on a graph, then you use the original function f of x. That's what it's for. Okay. How does it tell you that? Well, basically, you plug in x and compute y. You can also realize that if your y equals f of x, it means x comma y is a point on the graph. So that is what the original function is for. So if I'm ever asking you a question where I ask you something, for example, find the equation of a tangent line. You know, to find the equation of a straight line, you need a slope and a point. To find the point, what you should be using is the original function. You would not use the original function to find the slope, for example. You'd only use it to find points on a graph. That's what it's for, right? And you wouldn't use it for another purpose. F prime of x is probably a function that a lot of you have seen for the first time in this class. So what is the point of that function? Well, this function can give us various kinds of information. There are 4 different pieces of information that we can get from the derivative that will be useful. One, it will tell us if f is increasing. That means it can tell me if what I'm measuring is getting larger over time, or is the graph moving up as I go from left to right. It can tell me about if f is decreasing as well. It can also tell me about maximums and minimums of the function. So if I ever want to figure out one of these 4 pieces of information, of course also the slope, rate of change. But graphically, the first 4 is what I'm talking about. So if I ever want to figure out these 4 pieces of information, if I want to figure out the slope of the function, or I want to figure out where there's a maximum or a minimum to the function, where is the function increasing or decreasing, I would use the first derivative to tell me about that. Right? That's what the first derivative is for. In terms of maximums and minimums, the main point to take away here is that in general we don't actually know how to do this for general functions. There are some functions that are nice, like quadratics, where we have a formula that gives us the maximum or minimum, i.e. the vertex formula, but that doesn't exist in general for general functions. You really need something like a derivative to talk about that in general. How does the derivative tell us about this? Well, one, we know that if f prime is greater than 0, that means our function is increasing. If f prime is less than 0, that means our function is decreasing. How do we know about maximums or minimums? Is in the following. Look at a maximum. We have a max at y equals f of a if the following happens. We have a point A. To the left of that point, our derivative is positive, meaning our function is increasing. To the right of that point, our derivative is negative. That means it's decreasing. So you're going up on this side, you're going down on that side. And of course, in the middle, you have to exist. There has to be a point there to be the maximum. So at A, f is continuous. F prime would be equal to 0 or undefined. I put or undefined because it can be a sharp corner, for example, but it would still be the highest point in a region, whether or not it's a sharp corner. Okay? So if we have a point where that is defined in our function, and the derivative is positive on one side and negative on the other side, in that order, we've obtained a maximum point. It means we went up and then we came down, so in that middle we were at we attained a highest point. Minimum is pretty much the same, but it's sort of course, the opposite. So we have a minimum at y equals f of a if the following happens. So at A, again, f is continuous, and the derivative is equal to 0 or undefined. On the left, though, our f was decreasing, so we're decreasing as we go towards A. And on the right, our derivative is positive, which means it's increasing as we leave A. So we're going down, and then we pass A, and then we start to go up. It means that at A, we hit a minimum point. A would be the lowest point. As long as there's actually a point there, it has to be, the function itself has to be continuous. In terms of slope, f prime is the slope. Right? It's a formula for the slope of the function at any given point. But this is the information that we can get from this function. Whether it's increasing or decreasing, whether we hit a maximum or minimum, we can determine from the first derivative. And this is how we do it. Notice that this would involve solving inequalities, which we've done before. This requires testing intervals, which we've done before. It's actually algebra that's being applied here. The calculus is you knowing when to use the function for what purpose. Right? So if you want to find out where a function is increasing or where there's a maximum or a minimum, you would not use the original function. You would use the derivative to determine that. Right? If I want to find a point on a graph, I would not use the derivative. I would use the original function to determine that. Right? Each function has a different purpose. They tell you different things, and there's a specific way in which they tell you these things. You have to know this moving forward. Is anyone still copying? So in your notes, you can put another row here. There's going to be a third row below this, but I won't have space, so I'm going to put it in. We're going to move on to the second derivative and what it tells us. So f of x is points on the graph. F prime of x is increasing, decreasing, maximum or minimums. And then we have the second derivative, which is the guy we looked at last time. So this guy we use the second derivative when we want to figure out things like concavity. Remember, there are two versions. You can be concave up or concave down. It's really to talk about the shape of a graph. So do you shape like a smiley face or a frowny face? That's concavity. It's also a measure of how the slope is changing. We can also use the second derivative to talk about inflections, which is a point where concavity changes. And I gave you some examples last time of applications to that and how you can interpret that in various contexts, like plotting sales or measuring the number of cancer cells in someone's lungs or whatever. These can mean different things, right? But when you're after one of these two things, you use the second derivative. You can't use the first derivative to figure out concavity. You can't use the original function to figure out concavity. Use the second derivative to figure out concavity. And how would it tell us concavity? If the second derivative is positive, that means it's concave up. Remember, concave up like a cup, that means its shape is that. Which means if it's increasing, it would be increasing at an increasing rate. And if it's decreasing, it would be decreasing at a decreasing rate. That's what concave up would mean. If it's negative, this gives us concave down. That means you're shaped like a frowny face. Meaning if you're increasing at a slower rate, you increase by less over time. Whereas if you're decreasing, you decrease at an increasing rate, which means you decrease by more over time. And so that would give you a concave down behavior. In terms of inflection, at y equals f of a, this is what would have to happen. So at a, f is continuous, f double prime is 0 or undefined, and f double prime changes sign. On either side of A, meaning it switched from a positive to a negative or a negative to a positive. In either case, you will obtain what we call an inflection point. There was another application which I told you to motion, which I'll give you some examples later on. But this guy is what would give you position. This guy is what would give you velocity. That's just speed in a particular direction. This guy here will give you acceleration. So there was also that interpretation on top of it. But in terms of graphically speaking and conceptually speaking, each of the functions that we've looked at so far, they tell us different informations, and we can extract this information in different ways. So if you're looking at points on the graph or certain outputs, we're looking at the original. We're looking to figure out whether we're increasing or decreasing, where maximums or minimums are, we look at the first derivative. We're looking for concavity or inflections, we look at the second derivative. You don't look at one of the other functions for one of the things that it's not supposed to give you. Okay? So if I want to find a point on a graph, I'm never going to look at the second derivative. That's not what it's for. I don't look at the second derivative to figure that out. You look at the original. Right? So there are going to be times where we're going to be having to find multiple things. You need to know which function you need to look at to find which thing. So that's very important. And with that, we've kind of wrapped up 2.3 and 2.4. So the homework for that is due next class. So we're very conceptual in 2.3, 2.4, but I think the ideas behind what we will be doing are important. And they're important enough to really focus on without being distracted by too many examples. So, don't worry, we'll be doing tons of examples following this. Chapter 3 is all about that, by the way. Chapter 3 is all about finding formulas to do a lot of computations. So chapter 3 is going to be very computation heavy, and we're going to learn all sorts of rules to find derivatives a lot quicker. So let's move on. Start 3.1. We're going to talk about some derivative formulas and properties. So formulas refer to, for specific functions, we'll know how to find the derivatives right away. There will be a rule to deal with specific functions. And properties is talking about their algebraic properties in terms of how they distribute or what kind of algebraic properties a derivative has. Let's start out with properties. Two main ones we care about. So let's C is a constant. F prime and G prime exist. Then we have one property that's called the constant factor rule. This is a property that says we can factor constants outside a derivative, meaning if I'm taking the derivative of a constant times a function, it is the same as me taking the constant and then multiplying by the derivative of the function. This is called the constant factor rule. We can factor constants out of derivatives. And you only need to look at the limit definitions to realize why that's true. This was actually something we could do with limits. Limits we can always factor constants out. So with a derivative we can factor constants out. Second property is the sum difference rule. This is basically the rule that tells us derivative distribute across sums. So if I'm taking the derivative of a sum of functions, I have a function f of x plus or minus another function g of x, then I can take the derivative of a sum by taking the derivative of the individual elements in the sum and adding them together. In other words, a derivative will distribute across a sum. It has a distributive property. So to differentiate a sum, it's just the sum of the derivatives. This is not true for products or divisions, right? So with limits, we could actually distribute across products and divisions, but derivatives do not do this. And that's because of the formula when you plug in that f of x plus h minus f of x all over h. It doesn't work with multiplication very well. because it has two terms in it, so when you multiply, there's a foiling thing going on, and so it doesn't really work as nicely. It works very nicely with constant factors, it works very nicely with sums, it distributes, but if this was a multiplication, it doesn't follow, it doesn't work. We'll talk about multiplication later. But these are the two important properties that we're going to be talking about. Let's go to some formulas. So some of the formulas I'm going to actually prove for you because I want you to see that they don't just pop out of nowhere. But just a couple, just take my word for it that these are true. So the first formula is talking about the derivative of e to the x. I think I mentioned that before. Or why the function e to the x is a very nice function. The answer is because its derivative is itself. And it's the only function who a constant times itself is its own derivative. 0 is the only other function that does that, so this function is unique among all the functions we've studied in terms of derivatives. No other function other than 0 will have that property. That a constant times the function is the derivative of the function. Like to find the derivative, it's the function itself. In other words, the output of the function is the same as the slope of the function at any given point. This is one of the few non-zero, this is the only non-zero function that has that property. It's a very important property. At this point, it's something that you should have memorized. I proved it for my Math 1207 class, so if you're interested, you can watch the video for that, but I'm not going to prove it for this class. I don't think it's going to give us too much insight here. But that's the rule you can know. The derivative of e to the x is e to the x. Also, by property 1, the derivative of any constant times e to the x is also itself, right? So if I want to find the derivative, example, of 7 e to the x, then that's just going to be 7 times the derivative of e to the x. But derivative of e to the x is just e to the x. So derivative of any constant times e to the x is also just itself. Right, so you can use the constant factor property there. Another rule, which we'll revisit this rule in 3.4, but I want to actually use it to prove some things because it's easier to prove with this rule. Kind of a big deal. It's called the chain rule. Super important rule. It's one of the fundamental derivative rules. We'll see this again in 3.4. But I'll literally be using it all the time up until then. A lot of things are just easier if I have this rule to use at my disposal. The proof for it is a little bit subtle, so I won't prove it either. You really need a deeper understanding of limits than we've done in this class. So at this point, just take my word for it. Might be a little confusing to start out with, so don't worry if you're totally confused. I'm going to be telling you about this in 10 minutes. But we will go over it a lot, so try to get it, but if not, you have time a little bit. So it talks about to differentiate composite functions. So I'm not just differentiating f of x, I'm differentiating f with a function plugged inside of it. Okay? So this is the rule. The rule says you differentiate the outside function, leave the inside function alone, then multiply by the derivative of the inside function. So it turns out that's how you differentiate a composite function. You differentiate the outside, then multiply by the derivative of the inside. That's the idea. Let me give you an example with that. differentiate the square root of x squared plus 1. So that's something a little bit more complicated than we've looked at so far. So far we did the limit definition to find the derivative of x, the derivative of a constant, derivative of x squared, derivative of radical x. But something like radical of x squared plus 1 is a little bit more complicated than those guys. And you can imagine that putting that into the limit definition would be sort of annoying to calculate. But yeah, here, one thing is to realize that, do I have color? Notice what is happening with this function here. It's like I had a function f of x was the square root of x, and then I had a function that's g of x, which is x squared plus 1. Then if I were to find the function f of g of x, what would that be? Well, you take this guy, plug it into that guy, and so you end up with this guy. So the idea is you wouldn't just look at this as a function itself, you'd look at it as some function plugged inside another function. So there's a radical, but it's not just radical of x, it's radical of something else, right? There's something there instead of just an x. So really this guy would be thought of as a composite function. And so the chain rule says I'm going to differentiate the outside function, so I'm going to take the derivative of radical x, which we know how to do, by the way. We do know that the derivative of radical x, what was the derivative of radical x?
1 over 2.
1 over 2 radical x. We did that last class. Do I know about the derivative of x squared? We did that last class as well. Derivative of x squared was?
2x.
2x. And the derivative of 1?
0.
Right, we know that derivative of any constant is 0. So individually we know about the derivatives of all these functions, but when you kind of mash them together, how do you find the derivative? It turns out you use what we call the chain rule. And so what we can do here is to realize that there is an outside function of the radical, but we know how to deal with that. It's 1 over 2 times the radical, right? Now in the first part here, it's the derivative of the outside, you leave the inside function alone. So I know the derivative of radical x is 1 over 2 radical x, so it's derivative of radical blah is 1 over 2 radical blah. Leave the blah alone in the first case. Then what you're going to do is you're going to multiply by the derivative of the blah, the inside. So you're going to multiply by, and we can put in parentheses here, the derivative of x squared is 2x, plus the derivative of 1 is 0. Right? And I notice here I applied the sum rule to do that. So the derivative of this function here would be 2x divided by 2 radical x squared plus 1. Right? Which you can simplify, you can cancel these guys out. Right? And that would be using the chain rule. Give you one more example. What if I had x plus the radical of x all squared? There are a couple ways to deal with this one. I could have just FOILed out, but we'll see there are issues with expanding parentheses later on. But what I can realize here is there's an outside function is the square, and the inside function is x plus radical x. So the chain rule says we can differentiate that by differentiating the outer function. So how do I differentiate something squared?
It's 2x.
2 times the thing, right? The derivative of something squared is 2 times the thing. We derived that before. So it's just 2 times the thing. So derivative of x squared is 2x. And then we multiply by derivative of the inside, which is again parentheses. Derivative of x is 1 plus derivative of this is 1 over 2 radical x. And so that would be the derivative of that function. Hopefully you can appreciate, had you done the limit definition for this, getting to that answer, you can imagine would have been quite common. But it's not that bad here. So chain rule is very important. I introduced it early. Really, it shows up in 3.4, but I introduced it early because I want to use it to do some other things with it, which we will do next time. We'll stop there because that was the last example I did in that last class. So yeah, starting next class, things are going to start to move fast because we're going to learn a lot of formulas by which we can do things very quickly. Homework 2.3 and 2.4 is due on Friday, and I will see you guys then.